Hello everyone, my name is Mengfan and I'm a research fellow in Cambridge founded by the Royal Society. I'm very honored to give this seminar talk about studies on polytopology in ferroelectric polymers. I would like to thank my supervisors, collaborators, and generous funding bodies for all the help in the mentioned work. And I'll explain the fundamentals about topology and ferroelectric polymers and explain how these two can be combined in the first part. And then I'll explain how we achieved topological field manipulation and give conclusions and perspectives. So when we refer to the term topology, we are actually referring to the topological soliton or defect that can conserve certain charge against the external field. In a very classic case of a domain wall, it can be driven to move while the head-to-head or tail-to-tail configuration can still be preserved. Other intriguing topologies have also been discovered, mostly in magnetic materials such as vortex or skyrmion. So let's take magnetic skyrmion as a classic example to explain how it can emerge in material. It is generated intermediately under finite magnetic fields between the Helix ground state and the uniform ferromagnetic states. So in TEM images, people can observe its generation and annihilation and summarize its phase diagram. But for ferroelectric materials with spontaneous polarization, it is quite difficult to have the non-collinear states because two nearby polarization, if they have unparalleled arrangement, there could be uncompensated charges in the space, and that is not favored by energy. So for a long time, uniform alignment like ferromagnetic states has been dominant in ferroelectrics. But in recent decades, people realize that we can take advantage of depolarization fields. So normally, a ferroelectric material exhibits striped domains with domain walls instead of a large single domain to minimize the depolarization fields. But at the edge of the domain walls in an insulative surface, there can be stray field, and this stray field may become expensive in energy if the size of the ferroelectric is reduced to nanoscale. And in this case, domains with lateral polarization can appear to yield flux closure structure, and this might further turn into vortex or skyrmion-like polar structure with continuous spatial rotation if the strain can be applied through substrate to reduce the anisotropy of the ferroelectric, and they have been experimentally observed in the oxide superlattices. But regarding the polymers, there is a significant difference in the origin of ferroelectricity. So in oxide, they form bonds with large ionic component, and the polarization mainly comes from displacement. The positive and negative ions displace against each other, and we have a polarization in the proper ferroelectric. But for polymer, they form covalent bonds, and because atoms have different electronegatividity, the bond exhibits a dipole, which is permanent as long as there is no chemical reaction. So here, in the chain of polyvinylidene fluoride, which is a well-known ferroelectric polymer, the orderly aligned atoms and dipoles produce a polarization. And in the crystal lattice of this PVDF, which is orthorhombic, chains are aligned along a unified direction. And if we apply an electric field to switch the polarization, all polymer chains will be rotated collectively to complete such a switching. So there is a rotational degree of freedom. This degree of freedom can be fully exploited in the copolymer of vinylidene fluoride with trifluoroethylene, which can be regarded as some hydrogen being replaced by fluorine to facilitate the formation of this straight chain and to increase the crystallinity. So the copolymer can crystallize into a single crystal with the shape of a lamella, which is just called as lamella. And the thickness cannot be larger than 100 nanometer, but it could be much larger in the lateral dimension. So within it, polymer chains are aligned parallel to the thickness direction. Therefore, the molecule and polarization mainly rotate within the lamella plane. So in most research, people like to produce vertical lamella, which has higher polarization outer plane and with lower coercive field. But at some point, we started to wonder why don't we just lay the lamella down? Because with this, we can actually see clearly how the polarization is organized, and since the polymer can rotate, there might be something curvy, and this indeed led us to something. So first, we found that when the thickness is decreased down to 1 micron, there could be face-on lamella stacking in the film, after they are fully crystallized through a melt recrystallization treatment. By further reduce the film thickness to around 100 nanometer, we observe a single layer of lamella from the surface morphology, and we use PFM to detect the in-plane polarization. There are indeed something circular in the polarization. So if we look closer into a circle, we found that we have banded structure in a concentric pattern surrounding the circle in the center, and they are all filled with stripe domains. So in the center is just some normal stripe that can be expected from the crystal lattice of the polymer. But in surrounding bands, the stripes are perpendicular to those in the neighboring bands, and because the bands are circular rings, all those stripes just rotate, rolling with their angular position. We confirm that all these stripes are antiparallel, so domain walls between stripes are with 180 degrees. Therefore, we can quite confirm that in our sample we got ferroelectric order because the existence of the domain. Meanwhile, we got them organized in concentric rings, so we got coexisting toroidal order. We also look into the thermal evolution of the domain state and found that the stripe disappear when rise in temperature across the Curie transition. So it's natural that we lost the ferroelectric order, but the toroidal feature is still preserved in the paraelectric phase until the film is completely molten. So therefore, the Curie transition is where the two order parameters can be organized into the same domain state. One thing quite particular about this Curie transition is that the lattice change is quite large. The spacing along the direction perpendicular to the polymer chains in the paraelectric phase is much larger than those in the ferroelectric phase. So when we got our lamella laid down into the film and annihilate from high temperature, they would undergo a transition where all crystallized tend to shrink, but they cannot because they are continuous and clamped by the substrate. So instead, there should be a biaxial tensile strain at room temperature. So this is further confirmed by our measurement in strain-free sample and the films, and we can calculate the tensile strain around 7%. To elucidate the effect that strain can have, we apply first principle model to calculate the free energy of polarization along different directions under a series of strain conditions. We found that the energy barrier of different polarization at different direction is much decreased. It was 82 milli-electron volt at zero strain and quickly decreased to less than 1/3 of it at strain of 8%. So with finite strains, all polar directions become nearly the same expensive for the same chip in free energy, instead of confining polarization along a few discrete angles. So this degeneracy energy landscape should allow the continuous rotation to happen. So then we think about how we can manipulate this topological thing. In current literatures, mechanical and electrical fields have been applied onto oxide superlattices with polar topology to manipulation. With this stimuli, the topologies can be annihilated, for instance, to monodomains by electric field, or to a domain with in-plane polarization by compressive force. So they are actually destroyed, and we observed all or nothing manipulation through phase transition from a toroidal phase to a non-toroidal phase. This is quite different to the manipulation paradigm for magnetic material, which is away from the phase transition. So take skyrmion again, for instance. When a single skyrmion was generated, it can be moved by current. And if a skyrmion lattice is generated throughout the material here, a current may even generate their collective rotation. So in both cases, these topological objects are just simply moved, not being destroyed and then regenerated by reversible phase transition. One thing that can make the difference is that the magnetic ground state is chiral, so toroidal topology can be protected at small finite field, but this is not certainly the case in polar oxide where the ground state is actually just achiral. But this can be quite different in ferroelectric polymer, as I introduced. The high temperature phase already exhibit toroidal feature and potentially chirality. And we found that the high temperature phase should exhibit a helical chain conformation, and from the phase diagram of the copolymer, we found that this chain conformation can be maintained if we decrease the content of the former monomer, the VDF. So we choose a polymer within the middle region, which should exhibit a mixture of the two phases. The two monomers have equal molar amount in this polymer, and after we fabricate the film, we notice most area of the sample exhibits curly stripes. But in some places, the stripe just get assembled concentrically, forming a region with net scale in 1 micron. So according to angle-resolved PFM images, we got precision map of the microregion. When expressed by color, is concentric, but in arrows, something else can be observed. So we obtain the curl and divergence of the microregion, which all exhibit spiral feature. So the truth about this microregion is that it has a polar skeleton, which spirally flows in and then out, represented by the red and blue arrows here. And between the skeleton, there are white arrows rotating in a near sequence. We define the polar spiral as counterclockwise spiral. You can tell from the sense of the rotation when either blue or red comes from in to out. It is also an important signature that if look from the center to outside along any radial direction, the near rotation is also in counterclockwise sense. So symmetrically, there can be clockwise polar spiral, and we also observe them in our sample. It is quite amazing that we have a topology which is asymmetric in two-dimensional space. To see the effect of field manipulation, we try to apply electric fields or stress individually through PFM tips. The field can only be effectively applied to a very small region beneath the tip, but because we can scan the tip across the whole region, the field was uniformly applied to the sample. And what we observe from later PFM is that now the domain wall migrates toward the center with the increase of the field magnitude. And if we look into the polarization represented by its curl, we notice that the polar spiral just got rotated along in plane directions when we drive it by out-of-plane fields. So we found that the clockwise spiral can only rotate in clockwise sense and vice versa. So for electrically driven rotation, the sign of the voltage doesn't matter, so it's probably mediated through electrostriction. And note that we observe the rotation after withdrawing the fields, so all these changes are non-volatile and continuous with the field increasing. So when we apply relatively small electric or mechanical field, the polar spiral can be preserved and meanwhile rotated, and it can be destroyed by larger field, turning into a monodomain by electric field or stripes by mechanical fields. The typical field required for annihilation is about twice the field to achieve evident rotative manipulation. So in this case, we indeed achieve a manipulation well below the phase transition for topological objects. We did an infrared mapping on film using the beam which is resonant to the non-helical phase, and we confirmed that the helical chain should be mainly distributed in the polar spiral. And according to our X-ray scattering results, none of these phases was subjected to macroscopic strain, like the material shown in the earlier part. So back to the helical chain itself, it is not surprising that they can induce something unparalleled because they are chiral, with two kinds of helicity, right or left. One of them, which is left-handed, is chosen to do free energy calculation along different directions. They exhibit less energy when rotated collectively in one sense than the other. This suggests that the polar interaction is already asymmetric. We then calculate the free energy, relative free energy of a pair of helical chains. Each of them is rotated independently by an angle. So from this map, we can see that the lowest energy point is not on the line where alpha 1 equals to alpha 2. We also notice that the local lowest energy point falling into the same side with the global lowest energy point, verifying that for this material, for the left-handed chain, the alpha 1 always tends to be smaller than alpha 2. So for a pair of chains, if they are expressed by a pair of arrows, they tend to be aligned like this. And if we have an alpha 3 and only consider the pair of alpha 3 and alpha 2, it should be further tilted. So if it goes on, we have a neo sequence in one sense. And don't forget, this is from the one type of chiral chain. And if it's the other right-handed one, the map should be exactly mirrored by the line of alpha 1 equals to alpha 2, leading to the conclusion also in mirror. So that should indicate how the different neo rotation and spirals are favored to be formed and can be preserved under a field, leading to the manipulation more than just the destruction. So, as conclusions, we first align single crystal ferroelectric polymer, finding that strained film can exhibit spatial rotation. But then, by looking into the polymer film without strain, but with an unusual chain structure through compositional optimization, we find a polar spiral that can be electrically or mechanically rotated using relatively small fields. Something more than the polymer material is that they have rich response in infrared and terahertz range, resonant with the vibration of covalent bonds. So these bonds contain dipoles, and the transient dipole induced by the movement can observe the light depending on the direction of the electric field of the light beam. So that's why we can observe different spectra when changing the polarization of the light beam on an aligned sample. So one possible usage of this topology in polymer is to modulate the light pattern and encode it, because when polarization are rotating, the molecule alignment is also changed, and the terahertz dipole might have a non-collinear distribution. So we indeed verify that there is a toroidal feature in the response pattern on far infrared light beam, and meanwhile it can be manipulated by applying external fields to the sample. So that's all. Thank you so much for your listening.